Welcome to the Celebrated Achievers Mentorship Program, CHAMP. We are bringing academic dreams to reality. So in this video, we'll be talking on chemical equilibrium. Chemical equilibrium. So I will be talking on the basic things you need to know, everything you need to know about chemical equilibrium. Then we will take all the past questions I have with me here. Oh yes, I will be using LAMLAD as my reference material. So we'll take all the questions there, so that you'll be fine towards the preparation of your exam. So let's get started. Chemical equilibrium. Now, what do we call an equilibrium? An equilibrium is a state where, yes, material is, or a equation or chemical reaction is said to be in equilibrium if no feasible change is observed. Yes, like let's say we have A plus B to give us C plus D. So it's always a reversible reaction. It's always a reversible reaction. Then another thing about chemical equilibrium is that it must be in a closed system. It must be in a closed system. Because if it's not in a closed system, let's say we have something like this carbon plus oxygen to give us what? CO2. Now, the idea of equilibrium is that as this carbon and oxygen is giving us CO2, CO2 must be decomposed to give us what? C plus O2. So the rate of forward reaction is always equals to the rate of backward reaction. That's a jam question. The rate of forward reaction in a system in equilibrium is always equals to the what? Rate of backward reaction. So now the system must be a closed system, so that now if this one is not in a closed system, in a closed container, now once the CO2 is formed, it will be released to the atmosphere, to be released to the atmosphere, and there will be no conservation. It will not be able to proceed to the backward direction. So it must be a reversible reaction. It must be in a closed system. And let me talk on the delta G for reactions in equilibrium. The delta G is always what? Zero. If the delta G is negative, it is what? It is spontaneous. I told you this already in the video on energetics. If this delta G is positive, it is what? Non-spontaneous. But if it is zero, it will be in what? In equilibrium. In equilibrium. Yeah. So please let's take note of that. The free energy change is always in what? In equilibrium. So and as we have two types of equilibrium actually, but we'll be dealing majorly with dynamic equilibrium. We have dynamic and we have static equilibrium. For instance, if you have two boys, this is an example of physical equilibrium that is that is static. Let's say we have two boys on a seesaw, yes, and they balance themselves. This is a physical equilibrium, and the physical equilibrium is static. Is static. Now let me just give some normal things. Let's say we have a reaction like this: A plus B to give us what? C plus D. Now in this reaction, for instance, if I'm to write the equation, the rate equation, now let me ask you, will A and B, will they be increasing? Okay, yes, let's say this is a forward reaction, not reversible. Now just forward. Let's say we have a reaction like this. Now will A and B, will they be increasing or decreasing? They will be what? They will be decreasing. The reactant is always decreasing, because this is not a reversible reaction. This is not a reaction in equilibrium. C and D, will they be increasing or decreasing? They will be what? Increasing, because they are the products. They will be increasing. So let me just give you this. For a reaction that is not in equilibrium, A and B, they are what? They are decreasing. So you use what? A negative sign. C and D, they are increasing. You use what? A positive sign. So if you are to write it, dA over dt negative is equals to dB over dt negative, because it is what? It is decreasing, is equals to dC over dt positive, is equals to dd over dt. What's the meaning of this? The rate, the dt means what? The rate. So the rate of formation of A is equals to the rate of formation of B, is equals to the rate of formation of C, and the rate of formation of D is actually the same thing with the rate of the what? Of the reaction of A and B. So this is actually not needed. I'm just using it to explain something. It's just for advanced level of chemical kinetics. Yes, let me go back to chemical equilibrium now. So I will quickly talk on equilibrium constant now. Equilibrium constant, and how to determine the equilibrium constant of reactions. Then after that, I will talk on some the Le Chatelet's principle, and then we'll take questions. So let's go to equilibrium constant now. Equilibrium constant is actually based on the law of mass action. law of mass action. The law of mass action is postulated by what? Goodbag and Wedge. Goodbag and Wedge. Yes. So what the law of mass action says that is that the rate of chemical reaction is proportional to the what? To the active masses, to the product of the active masses of the reactant. So this is it. Let's say we have a reaction like this: A plus B to give us what? C plus D. So he said R is equals to K, the product of the active masses. So what's the concentration of C? So this is it, RKCD. Do you get it now? So this is law of mass of this determination of equilibrium constant. So let me just quickly give you some things. Now in the equilibrium constant, we only deal with what? Gaseous and dissolved species. Gaseous and dissolved species. We only deal with this. You don't deal with what? Solid and liquid. You don't deal with solid and liquid. You only deal with what? Gaseous and dissolved species. Gaseous and dissolved species. And the number of moles must be taken to account. Let's say we have what? A plus B to give us what? C plus D. And this one is 2A, this one is 3C, this one is 2D. So if I'm to write it, R will be equals to what? K. What's your product? First product, C raised to power what? Raised to power 3. Then D raised to power what? 2. Over what? Your reactant will be at the lower side. A raised to power B. A raised to power 2. B raised to power what? 1. Do you get it now? Yes. Let's try for another reaction. Let's say we have something like this. A plus 2B to give us 3C plus 2D. Yes, reversible reaction. Yeah, just pardon this one. So can you try it out now? You can just pause it and try it out. I'm sure you have done it that now. So let's compare our answers. So you have what? K, C raised to power 3, D raised to power 1 over A raised to power 1, B raised to power 2. I'm sure you get how we did this. Yes. Now let me twist things now. Let me put the state of matter. Let's say we now have something like this. W plus X to give us Y plus Z. Let's say this one is 2, this one is 3, and others. Let's say this one is solid, this one is aqueous, this one is gaseous, this one is liquid. How will you write it? I said you consider what? Gaseous and dissolved species. So you can't consider this one because it is a liquid. You can't consider this one because it's a what? It's a solid. So you can only consider this one and this one. So your R will be what? K Y raised to power 3, right? Raised to over X raised to power 1. Do you get it now? You can't consider W and Z because they are what? They are solids and they are liquids. We can only consider gaseous and dissolved species. So take note of that. We only consider gaseous and dissolved species. We don't consider solids and liquids. Another thing you need to note very quick is try this one out. Let's say you have 3C plus 2D to give you 4E plus F. Yes, this one is gaseous, this one is aqueous, this one is aqueous, this one is liquid. What will be your answer? Pause it and try it out now. So my answer here will be what? R is equals to K E raised to power what? 4 over C raised to power 3 D raised to power 2. Do you get it now? Aqueous and gaseous and dissolved species. So you don't consider liquids. So take note of that. So I believe you can move on. Please, if you've not gotten it, just play back. Yes, let me quickly talk on let me talk on this first before I move on. Now we have two types of equilibrium. Yes, we can have homogeneous equilibrium. I think a question was set on this. We have homogeneous equilibrium, then we have what? Heterogeneous equilibrium. Homogeneous equilibrium is when the what? The reactant and the product and the catalyst, they are in the same phase. Let's say we have a reaction like this: A plus B to give us what? C. And this one is gaseous, this one is gaseous, this one is what? Gaseous. Then we have a catalyst too. Let's say NO, and this NO is also gaseous. So when the three are gaseous, the reactant, the product, and the catalyst, when they are all gaseous, we call that what? Homogeneous catalysis. Do you get it now? But let's say we have something like this: A plus B to give us what? C. And this one is gaseous, this one is gaseous, this one is gaseous, because there's a question on this, and the catalyst is solid. Will this be a what? Like ammonia process, for instance. I can remember that Java question: N2 plus 3H2. to give us what? 2NH3. Then we have finely divided ion catalyst, solid. This one is gas, this one is gas, this one is gas. They said, is this like the question was actually on homogeneous catalysis. So this is not a what? An homogeneous catalyst. This is not an homogeneous equilibrium, yes, because the catalyst is not in a gas. Do you get that now? So this is an heterogeneous catalyst equilibrium. Yes, the theory must be in what? Must be in the same phase. Okay, now one thing you must note is that let me quickly talk on this. Let's say we have R is equals to okay, let's say we have A plus B, no, or A to give us B. Yes. Now what's the rate of your, it's going in the forward and your backward. So let's say we have two rates. Rf is equals to what? The forward reaction, let's say we are considering the products only, is equals to K raised to power B. Rb is equals to what? K raised to power A. You know, this is our product for the reverse reaction. B means what? Backward or reverse. F means what? Forward. And we are considering only our what? Our product. So we first of all go like this. Forward, what's our product? B. Backward, what's our product? A. I get it now. Yes. So this is how it is actually. Now I can actually say that Rf over B, if I make K the subject of the formula, is equals to what? Is equals to Rb over A. Are you getting it now? Are you getting it now? So I can say something like this. I can say A RFA is equals to what? RBB. Don't mind my proving. Don't mind my proving. But they can ask. They can ask. So RF over RB is equals to what? B over A. You don't need the proving actually. But I want to use it to prove something that can be asked in exam question. You don't need the proving. I will just give you what you need. Yes. So if you check this thing out, so like the main summary, if you check this one out, you can see that Rf is equals to B over A. Rf is equals to B over A. So like the thing is just that Rf is is the multiplicative inverse of what? Of RB. This is what I mean. Let's say we have Rf now. Rf in this one is what? KB. Then times, what's the meaning of multiplicative inverse? Of times 1 over, what's RB? KA. So if you multiply this, you will get what? Rf is equals to KB over KA. So this is what I have here. So this is it here. So Rf is the multiplicative inverse of RB. So please take note of this. This is a jam past question. Let's read some questions on this before we go to Chatelet's principle and this. So let's go now. I'm coming. Question 1. A chemical equilibrium is established when, what's the answer? When the concentration of the reactants and products remain unchanged. So in equilibrium, they will do what? They will remain unchanged. Yes. The idea of chemical equilibrium is based on what? Based on what? The equality of the rates of the forward and backward reaction. The forward reaction is what? Is equals to the backward reaction. Are we getting it now? Yes. So they said, what's the expression for K in the following reaction? So what would that be? This is your G, is your product. So it will be something like this. G raised to power what? Raised to power 2 over, this one is also gaseous, E raised to power 2, then F raised to power what? 1. That's what? Option D. I hope you get it now. Your product G raised to power what? Raised to power 2 over E raised to power 2, then F raised to power 1. So that's why D is correct. Are you getting it? So we have question 4 now. Question 4. Don't mind the proving I did the other time. Just note the principle that the reverse reaction, the rate of the forward reaction and the rate of the reverse reaction are what? They are multiplicative inverse of each other. Yes, let's move on now. So we have the next one, question 4. The equilibrium constant for the reaction is what? So go. Everything is gaseous. C raised to power X, right? Then D raised to power Y over what? A raised to power A, B raised to power B. I'm sure you got that. So this is it. C raised to power X, D raised to power Y, A raised to power A, B raised to power B. Do you get that now? Yes. So let's move on now. How is the equilibrium constant for the forward reaction Kf equals to that of the backward reaction? Yes. If you want to do that, what will be your answer? Kf is the what? Is the multiplicative inverse of what? Of Kb. Do you remember that? Kf is the multiplicative inverse of your Kb. So let's move on now. The equilibrium constant expression involves what? It involves the gaseous and dissolved species. It involves gaseous and dissolved species. That's what option D. Species in aqueous solution and gases only. Species in aqueous solution and gases only. So that's just that. Let's move on now.